Good day, everyone. So for today is our topic is about simple harmonic motion. So that is the first topic in waves and optics. Now let's describe first what is periodic motion. When we say periodic motion, it is described when a vibration or oscillation repeats itself back and forth over the same path. So I will show you examples of periodic motion. For example, this one. Okay, we have here a spring, and then attached to the spring is a mass. You can see that this one oscillates. So it moves down and up, down and up again, and down again. So there is a restoring force so that it will move that way. Another example is when you have a spring mounted horizontally and the mass of the spring is negligible and the object of the mass, M, slides without friction on the horizontal surface. When the spring is at its natural length and exerts no force on mass M, then we say that the mass is in equilibrium position. And let's take a look at this illustration. So you have here a spring, and then you have the mass attached to the spring. When the x is equal to 0, the object is at its equilibrium position. There. And then we have here, if you are going to push this spring to the left, then it will move to the right, and then it will move to the left again because of the restoring force. The equation which can describe that is this one. The restoring force equals negative kx, where k is the spring constant, so it depends on the spring here, and x is the displacement. So you can see in the figure here, this is x, or positive x. Since our reference is x equals 0, here at its equilibrium position, moving to the right, we have positive x. And then moving to the left, we have negative x. Okay, take note that the direction of the restoring force is always negative the direction of the displacement. So that is Hooke's law. Now we have here an equation for simple harmonic oscillator, wherein I will show you later how we derive this equation. The energy involved for a simple harmonic oscillator is this. We have 1/2 kx squared, wherein this one is its potential energy or elastic potential energy, plus 1/2 mv squared. This one is its kinetic energy. When we derive the equation, you will have the velocity of the spring or of the mass spring system. Its velocity equals positive negative v naught, or its velocity at the equilibrium position. It is where the highest kinetic energy is located, square root of 1 minus x squared over a squared, where a is the maximum displacement, or we also call that as an amplitude, and x is the displacement in between the equilibrium position and the maximum displacement A. Another factor that we have to consider is the period, where in the period, for it to complete one oscillation is equivalent to 2 pi square root of the mass over spring constant. For the simple pendulum, we have here a massless string, and then a mass is attached here. Then we have the displacement angle theta measured from this equilibrium position. And then we have the tension. Here is the tension on the string. And then the weight acting on it is downward, which is equivalent to mass times acceleration due to gravity. Then we have here the restoring force, because when you move the pendulum, it will move towards this direction, wherein this one is equivalent to negative mg sine theta. Again, I will show you the derivation later. But as a summary of the equations for simple pendulum, The restoring force is equivalent to negative mg sine theta, where m is the mass, g is the acceleration due to gravity, theta is the displacement from the equilibrium position. Okay, this should be around or less than 15 degrees for us to have a simple pendulum. And then force, or restoring force, is also equivalent to negative kx. Yeah. And then we have the period equals 2 pi square root of the length of the pendulum, and then the acceleration due to gravity. Frequency, okay, the frequency now is the reciprocal of period. It is the number of vibrations per unit time. So we have 1 over period equals 1 over 2 pi square root of g over L. Okay, again, let's review some terms. T is equivalent to the period. So that is the time needed for one complete oscillation or vibration. While frequency is the number of vibrations per unit time.
Now I'm going to show you the derivation for the energy involved in simple harmonic motion, and also we are going to derive the equation for the velocity of the object. So again, simple harmonic motion, for example, you have here a spring which is attached to the equilibrium position. We will call that x equals 0 at the equilibrium. And then if it's compressed, then it has moved to the negative x. The maximum for that would be negative a. We can note it as the amplitude, or negative a. And then for this one, if it's stretched there to the positive, so that will be positive a. Now recall in your mechanics that the total energy of the system equals kinetic energy plus potential energy equals the total mechanical energy. In this system, if we are going to stretch it, it is a stress. And then if we are going to release it, it will be moving at this position. And it will also be at stress at negative x, or at negative a, the maximum when we compress this one, the maximum compression. Okay. Now, if we are going to consider potential energy, elastic potential energy equals 1/2 kx squared. We know that in mechanics, for example, you have an object here, and then it will go down. It will have its maximum potential energy at this point. 0 kinetic energy. But at this point, it will have the maximum kinetic energy. But the potential energy here is equal to 0. It will have maximum kinetic energy. However, the potential energy at this point is equal to 0. Going back to this one, when we have the maximum potential energy, then 0 ang kanyang kinetic energy. So at position A, positive A, we have kinetic energy plus potential energy equals the total mechanical energy. But here at point positive A, the kinetic energy is equal to 0. So what we have is only the potential energy. And we can express it as 1/2 k positive A squared, when it's stretched to positive A. So ang total energy of the system natin at this point is just equal to 1/2 k A squared. It only has its potential energy. Okay, take note of that. But let's analyze what will be the energy if it's at equilibrium. At this point naman, it has its maximum kinetic energy. Kanina, when it's stretched here, it has its maximum potential energy. Same at this point, but at the middle, it has its maximum kinetic energy. Wherein the potential energy at x equals 0, potential energy is equal to 0, the elastic potential energy is equal to 0, but its kinetic energy is at its maximum. So recall that kinetic energy equals 1/2 mv squared. Considering the point between maximum potential energy and maximum kinetic energy. It is a point x greater than 0 but less than a. Okay? Or also at x less than 0 but greater than negative a. Okay? So it's at this point, in between. They both have potential energy and kinetic energy equals the total energy. So that will become, potential energy is the 1/2 kx squared, whatever is the distance, plus 1/2 mv squared equals the total energy. Okay? At the position between the maximum potential energy and maximum kinetic energy. It is around this position. Yan. Dito. Dito. And then dito. Okay, what we are going to do with those equations is that we are going to use them to derive an equation for velocity. So let's use it. Again, take note that the total mechanical energy is conserved. So energy at point 1 that we are going to choose is always equal to energy at point 2. Considering that there is no friction and it will not be converted to thermal energy. So we have, at point 1, wherein we have the maximum potential energy, 0 kinetic energy, and at the midpoint, or at the point in between the maximum kinetic energy and maximum potential energy, we have potential energy at point 2 plus the kinetic energy at point 2. Based on our derivation, we have 1/2 Ka squared as our maximum potential energy. That is equal to 1/2 Kx squared, that is the potential energy at x, or any position x, except x equals 0 and x equals a or negative a. Then plus kinetic energy is 1/2 mv squared. Okay, we are going to derive an equation for velocity v. Okay, so let's derive an equation for v. We now have 1/2 Ka squared minus 1/2 Kx squared equals 1/2 mv squared. So we can actually multiply everything by 2 and divide everything by m, so that we will only have v here. So multiply everything by 2, divide it by m. So what we will have, since we multiply natin by 2, 2 will be cancelled out. So we now have Ka squared minus Kx squared equals v squared. Pero we have here 1 over m. Okay, 1 over m. There. But we can cancel m here and 2. So we have v squared. Then we can even factor out k. So what we now have, I'll erase this. Let's factor out k. We have k over m, a squared minus x squared equals v squared. And the next is we can even factor out a. And now we can also factor out a. We can have k a squared over m. But since we factored out a here, this will become 1. And then this one, we should retain this one. Kaya dapat x squared over a squared. So that when you distribute it again, it will become a squared And then when you distribute it, it will still become x squared. Okay? So that is v squared. So we have ka squared over m times 1 minus x squared over a squared equals v squared. Okay. Take note of this. And also, recall that at point O, we have the maximum kinetic energy. So our energy there is equal to the kinetic energy, which is equal to 1/2 mv naught squared. To note its velocity at x equals 0. But at point, let's say, positive A, the maximum energy there is the potential energy. So we have the energy is equal to the potential energy 1/2 Ka squared. So we'll derive a relationship between this one. Okay, again, we'll derive a relationship between these two. Di ko muna i-erase ito. Okay? Let's divide our cute whiteboard. Yan. So, since energy is conserved, at this point, the total energy dito is the same as the total energy at this point. If we have chosen E1 equals E2, so they are the same. So, that will be KE equals the potential energy at those points. So we now have the kinetic energy 1/2 mv naught squared at x equals 0. Then the potential energy when x equals positive a equals 1/2 Ka squared. So looking at this, we can derive an equation which is related to this. So let's derive an equation for V naught. V naught squared equals 1/2 Ka squared. Then multiply ko sila. Tatanggalin to, multiply it by 2. And then divide it by m. So we can cancel out 2. We have an expression now for V naught squared equals K over m A squared. Okay? Nagkakaroon ba ng liwanag? So, I want you to look at that expression. And saan yan the same dito? Alright, very good. So, we can now express this in terms of the velocities. So, here. Yan. Tanggalin ko na ulit ito. Based on this one, anyway, yung complete derivation is also found in the module, but I think I have to explain it here. So, Ka squared over m is equal to V naught squared. We now were able to derive an equation relating the velocity at x equals 0 and a velocity at the point in the middle of the maximum potential energy and the maximum kinetic energy. So, we have this is equal to this. So, V naught squared, 1 minus x squared over a squared equals the velocity squared. Getting the square root, ituloy natin. Burahin ko muna. We now have V squared equals V naught squared 1 minus x squared over a squared. There. So we have to get the square root so that we can get V. Get the square root of both sides. So we have V equals, syempre the square root of this could be a positive or negative V naught. Then the square root of 1 minus x squared over a squared. Okay. So that is our equation for the velocity of a simple harmonic oscillator. So this one is a velocity of a simple harmonic oscillator. Okay, good. Simple pa lang yan. So, I hope you got the derivation correctly. Okay, now let's relate velocity to period. Okay, for period is defined as time needed for one complete revolution. If you have a circle, for it to have one complete revolution, that is period. But the distance that it has to cover for one complete revolution is equal to, distance over time pa rin, but the distance that it has to cover or it has to travel is 2 pi r, which is our circumference, okay? Over the period, the time needed for one complete revolution. But we can also represent r as related to our simple harmonic oscillator. The V naught equals 2 pi times the amplitude over the time needed for one complete revolution, okay? Period equals 2 pi a over V naught. So that's a relationship. Wherein recall also in the derivation that we had, recall that we have V naught squared equals K over M A squared. We will derive an equation for V naught, so square root both sides. We now have square root of K over M and A. Now I will substitute this V naught to this. So you now have period equals 2 pi A over square root of K over M, then A. So cancel na ang A. Our period now becomes 2 pi square root of, get the reciprocal of this, square root of M over K. Yeah. So that's another equation for period. Take note of those equations. Yeah. Period equals 2 pi square root of M over K. Okay, this time we are going to derive our equation for simple pendulum. Okay, for a simple pendulum, we have here a suspended mass using a string with a negligible mass. And then, of course, we are also assuming that there's no friction affecting it. Then we have here the angle measured from this position or the equilibrium position. If it's displaced, or we call it displacement, if it is displaced at a certain angle, and then it will be moving back and forth. Okay. Now, what are the different factors affecting it? This one is the length of the pendulum. Okay. We have, of course, the tension on the string. If we are going to raise this one and release it, what will be that restoring force? Just like in the simple harmonic oscillator, now we have the spring. But for this one, what will let it move like that? It's not downward, but at the diagonal. So let's analyze that. Recall that this one is the mass or the weight. Okay, that is the gravitational force acting on the pendulum bob. That is equal to Fg or equivalent to mg. We are going to analyze this. The angle here or the displacement here is the same as this one. Then we have another arrow here. So this is the force so that it will move this way. Okay, it's not the gravitational force because the gravitational force is pointing downwards, but it is this force. Now, how do we derive that force? Since in our illustration, this now is our hypotenuse. This is our adjacent side. If this is the angle, and this is our opposite side. Now, how do we get this one? Okay, that is our restoring force. Now, if we are going to draw it, draw another triangle. I'm going to draw another triangle here. Yan. Parang nirotate ko lang siya. This one will be our mg. And then this one will be our angle. And then we are looking for this force. Okay? So that force, since we have sine theta, this is the opposite side, opposite over hypotenuse. So our opposite side is the one we are looking for, let's say x, over our hypotenuse is mg sine theta. So that force is equivalent to mg sine theta. That is our restoring force for a pendulum. Since our displacement is less than 15 degrees, we can now consider that theta is approximately the same as sine theta. So our force now could also be expressed as mg theta. So there will just be a small difference of theta and sine theta if the angle is less than 15 degrees. And we are going to consider the angle less than 15 degrees so that we can have a simple pendulum. And take note of that, mg theta. Let's have another illustration. This is L. This is theta. There. Now the arc length. Let's also consider the arc length R. Recall also that arc length is equal to R theta. So for this one, our arc length is equal to L theta. So let's consider this arc length as x equals L theta. So our theta could also be expressed as x over L. So you have here the arc, or the arc length, and then the L, which is the radius. So another equation for this is that F could also be mg x over L. Since it's a restoring force, we can consider it as negative. Yan. Okay, recall also that we have a period, our formula for a period equals 2 pi square root of m over k. Now, we can derive an equation for a period of a pendulum. Now, again, our restoring force is F equals negative kx. For in the case of our pendulum, equals F equals negative mg x over L. So looking at the equations, we can now represent k as mg over L. Okay? So our k equals mg over L. So substituting k here to this one, it will become, burahin ulit natin, di na kasya sa board natin. So we have now formula for period of a simple pendulum equals 2 pi, then square root of m over this k, mg over L. I'll cancel this one. So finally, we have an equation for period, which is 2 pi. Since nasa baba siya, we can get the reciprocal, square root of L over G. Okay? So the factors affecting the period of a simple pendulum, how long it takes for the pendulum to move or to have one complete revolution, is equivalent, or is affected, it is affected by the length of the pendulum and by acceleration due to gravity. Now, you will also try to discover that in your experiment about simple pendulum. Okay? Okay, class, so that is our derivation for simple pendulum and simple harmonic oscillation. We haven't solved any problems yet. Those are just derivations. So, hopefully, naintindihan yung how we were able to derive the equations. Okay? Bye, everyone!